Hi everybody. So we're going to continue with kinetics, chapter 14, and last week we talked about the graphs, but we didn't talk about the rate laws that go along with the graphs. So we're going to start there. So remember we talked about a first order plot. You would graph your ln of the concentration of whatever your reactant is versus time. There is an equation that is associated with each rate law, be it first, second, or zero, and we are given information in these problems that we can plug in to those equations, and we can find things like how long a reaction went for, so that would be time. We can find initial concentration of something, final concentration of something, or we could find K, our rate constant. And we just need to be given the rest of that information in order to find them. So the integrated rate law is integrated from a regular, rate equals K A to the 1 if it's first order rate law. And then they integrate it, and then we get these equations. And here's one that's rearranged. I usually just stick with this one. Anywho. We already talked about units of K. So here we have a problem where we're going to use this equation, and you will be given these equations like this one and the second order one and the zero order one on your equation sheet. I'm just not going to tell you which one is first, second, or third, so you just want to remember that the ln is for first order reactions. Also remember that when we are doing these calculations on your calculator, you need to do ln and then second ln to do the inverse. And if you need help with that, you let me know. All right, so number 6. For a first order reaction, A goes to B, what will the concentration of A be after 600 seconds if the initial concentration of A at time 0 is 0.5 molar and your rate constant is 3.25 times 10 to the minus 3? Okay, so here we have K. We have A naught, right? Concentration at time 0. We have a time, 600 seconds, and we don't know what my final concentration is. So we have all the stuff that we need. If T equals 600 seconds, we have concentration of A at time 0 is, I think, a half a molar. And K is 3.25 times 10 to the minus 3 per second. First thing you want to make sure is that your units of time and your rate constant units are the same. You can't have one be in minutes and one be in seconds. They are the same, so we're in luck. My equation that I'm using, ln A is equal to negative K times my time plus ln of A naught, which is my initial concentration. Okay, so I have everything I need. I'm just going to plug in. This is my X. I don't know what that one is. So I have ln of A is equal to negative 3.25 times 10 to the minus 3 times 600 seconds. Notice those seconds will cancel, plus the ln of 0.5. Okay, so I can put all of that into my calculator and just solve for that side of the equation. So it's going to be negative 1.95 plus negative 0.693. All right, so my ln of A is negative 2.64. Okay, so I need to take the inverse ln of both sides. When I do that, I'm just going to have A here, and this is going to look like E to the negative 2.64. And that gives me 0.071 molar. And that's what I need I just need to make sure that my molarity has gone down because 600 seconds have gone by and my concentration has gone from a half a molar to 0.071 molar. So my concentration has decreased over that time. So at least that makes sense. Again, if you need help with your second ln button that's going to give you this little E, let me know. But that's how you solve. Okay, you guys, your turn. All right, you guys, there it is. Your concentration at 865 seconds is 0.018 with rounding molar. I guess the answer has 3 sig figs instead of 2. So if we were going to follow rules, it would look something like that. Either one, I would mark correct. So make sure that makes sense. All right, we talked about the graph already, so I'm going to skip over it. Here is our second order integrated rate law, which again is derived from a second order rate law. You integrate it, we get this. The equation here is what we're going to use for the second order integrated rate law. Okay, so here we have some information. We need to know, here's our time, 600 seconds. Here's our K, so this is the same as last time. And we have a same initial concentration. I don't know why I'm doing, oh, because it's C to D this time. All right, so here's K, here's the concentration of C, I guess. We can still call it A. Let's call it A just to make life easier, all right? So let's write down our information. We have T equals 600. We have K is equal to 3.25 times 10 to the minus 3, 1 over seconds. And we have our initial concentration is 0.5 molar. This time we're going to use the second order integrated rate law. 1 over the concentration of whatever is equal to, this is not negative this time. And this is your initial concentration. All right, so plug stuff in. This is what we don't know. So we got 3.25 times 10 to the minus 3, 1 over seconds. And we're going to multiply that by 600 seconds. And then we add 1 over 0.5. Okay, we do the math. I get 1 over A is equal to 3.95. So now I just have to take the inverse. So I do 1 divided by 3.95 is going to give me A. And I get 0.253 molar. All right, let's just make sure that this concentration has gone down from the initial. It has. It started out as, we've gone down by about a half. Started at a half a molar, now we're at about 0.25 molar. So we're good. So that's how you use the second order integrated rate law. Skip it. Remember that the second order is positive, so that's why we don't have a negative in our integrated rate law. Okay, the last one, zero order. This one's super easy. Here it is. All right, so now we get E to F. We determine that it's zero order. We want to know, again, what the concentration is going to be after 600 seconds. Initial concentration. Here's my rate constant. Let's write down my info. 600 seconds. 3.25 times 10 to the minus 3. 1 over seconds, concentration. I'm going to keep calling it A. It doesn't matter what we call it. My zero order rate equation is just the concentration of A is equal to negative KT plus the concentration of A naught. Okay, Let's plug in. Notice all these have been the same information, but because we have a different way that the concentration is influencing the rate, it's going to go faster or slower. If we solve, we end up with negative 1.45 molar. Well, that doesn't really make sense. How do you have negative concentration? You can't. So what does this mean? It means that the reaction doesn't take 600 seconds. The reaction takes less time, so the math isn't going to make sense. It's finished earlier. What happens after 60? I took up all this room with all those words. All right, well, let's do the same thing for 60 seconds. So we do this, and now we get perfect. Okay, that's a real answer. So it takes more than a minute, but it takes less than 600 seconds. And that's what we get after 60 seconds. If we wanted to know how long this reaction was, we would set this to 0, right? Because that's what you would want at the end, and solve for time. If we wanted to know how long the reaction was going to be. We keep our initial concentration and your rate constant. You just say that your final concentration would be 0, because that's when the reaction's done, and you just solve for T. That's 0 order. And here's your graph stuff. We talked about this already. All right, so let's go back to this guy. So for 0 order, first order, and second order, here is our integrated rate equations for each of the units of the rate constant, our plots, and then half-life we will discuss in a sec. But so here's all this stuff if you need to know it, or if you just need it organized for you. There it is. Just to remind you, like a 0 order plot means that when I double the concentration, nothing happens to the rate. So my concentration is 0 effect on the rate. The first order means that when I double my concentration, the rate will also double. So they have like a completely direct relationship. One doubles, the other one doubles. Second order means that if I double the concentration, I quadruple the rate. So it goes way faster. That's what that means. Just to remind you. Okay, we did this already. Okay, let's talk about half-life. What the heck's a half-life? So let's say you have this big block of carbon. All right, I have this cube of carbon in my hand, and it weighs 10 grams. And I'm going to hold on to it over time. There's time passing. And I want to wait until my carbon gets to nothing. So I'm going to wait until there's 0 grams of carbon. It's really difficult to know when an element has completely decayed to 0. Everything decays over time. Every element decays. Everything decomposes. Some of it decomposes and is radioactive when it decays. Some of it just decomposes into other things. They all decompose at different rates. So, you know, carbon goes at a really slow rate, whereas like I'm talking thousands of years would be its half-life. Whereas like strontium is it's 29 years, so about 30 years. And then you have certain elements that are really, really heavy that have like millisecond half-lives. So they decay really, really quickly. So if we were to determine how long it takes for 10 grams of carbon to go to 0 grams, how do you really measure when it gets to 0? You can, it's really hard. However, it's not really hard to measure when it gets to 5 grams, right? So now it's decreased by half of its weight or its mass. That is the half-life. So then I can say, well, carbon, say it's like, I think it's like 1400 or I don't know, there's a 1 and a 4, and I know it's in the thousands. So many years, right? So let's just call it 1400, just, I know that's wrong, but just for argument's sake. All right, and then you have, you know, say 10 grams of strontium. I know that one's 29 years to get to 5 grams. So basically it's the time that elapses from something to go from its initial amount to half its amount. And now you can start comparing how long stuff lives. So you don't want to start to like build buildings with something that has a 30-year half-life, because you're going to be in trouble in 30 years, probably before then. But anyways, that's what a half-life is. I probably wrote all over. I did. If you have a zero order reaction, here is the equation for half-life. Initial concentration, that's the rate constant. If you have a first order reaction, you have, this is first, you have this constant, 0.693, which is the ln of 2, divided by your rate constant. And if you have a second order reaction, here is your half-life equation, 1 over the rate constant times the initial concentration. Again, you will be given all of these on a equation sheet. You just got to know what's what. This is your first order with the number. That's just the ln of 2. This is 1 over, just like the plot is for second order. So that's how you figure out a half-life. Okay, number 11. We have iodine, and it dissociates at some temperature. Who cares? Not us. With a rate constant of 0.271 per second, what is the order of this reaction? How do we know? What's the order? It doesn't explicitly say, but how do we know? The units, if that's K, the rate constant, which it is, the units will tell us the order. It's first order. And we know that from the units of K. Half-life, so now we're going to go back and say, okay, here's my half-life equation. Okay, so the half-life, which is what this T1/2 is 0.693 over K. So I take, and this is 1 over seconds, so you end up with seconds as your answer, and it's about 2.56 seconds. That's its half-life. So at really high temperatures, iodine dissociates very quickly with a half-life of 0.256 seconds. So that means that if I have 10 grams of molecular iodine and I wait 2.56 seconds, I'm now going to have 5 grams of molecular iodine when I'm hanging out at 625 K. Which you wouldn't be, because you would die. Cool, next. So if we put all of this stuff together, and we have to kind of pick out the clues that will tell us what we need to know. All right, we have a reaction. Here it is. We have a plot that's 1 over AB versus time that produces a straight line. So what is this telling me? That tells me what my order is. And it has a slope of this number here, per molar per second. Well, you know what? This also tells me my order. And I also can get the rate constant from the slope. So I can get like all this information. Okay, what is a rate constant? Well, what's the order of my reaction? This says that I made a second order plot, second order. These units say second order. If I jump to B, it's second order, which means that my slope is equal to K. So my rate constant is this number. Okay, so now I got to write the rate law. The rate law only ever has the reactants in it. Rate law is rate equals K AB. This is second order, so that has to be 2. I have no other choice. What is the half-life when the concentration of AB is 0.25 molar? So I have to look at my equation. All right, I'm going to use my green. My T1/2 for this, because it is a second order, is 1 over K times my concentration initial. It gave me an initial concentration, so I know that T1/2 is equal to 1 over my rate constant, which is 0.772, times 0.25, which I got from part D. And when I do that out, I get 5.18 seconds. That's my half-life. Okay, that's how fast it decays in half. When AB is 0.25, here's my initial. What is the concentration after 100 seconds? So here's where I use this guy, my integrated rate law. KT plus 1 over A naught. All right, so I'm going to plug some stuff in. I do all the math. I take the inverse. My answer is 0.0123 molar. Just make sure you get that. It's like a lot of questions, but you can get most of the information from the beginning, and then if you can find the right equation to use, the other two are relatively simple to find. Okay. Perfect. Mechanisms. A mechanism will show you each individual step that a reaction takes in order to get from reactants to products. So sometimes you'll have more than one step, more than one transition state, when you have a more complex reaction. And so knowing the mechanism and every step that happens is usually a good thing, because then you understand how the reaction is happening. So if you let's say you're making a drug and you need to know how that drug is metabolized, and you don't know the mechanism of that metabolism, but then you have all these side products, you have no idea where they came from and attribute them to anything. So if you have something toxic in your drug and you need to get rid of it, and you don't know the mechanism of how that got there, then you're never going to be able to solve your problem. So mechanisms are actually really important in all sorts of chemistry to really understand how a reaction happens. And so people study them quite in depth. And so what we're just going to do is look at it sort of the way that we looked at Hess's law problems, where we're adding up stuff to make a final reaction. A mechanism will illustrate the individual steps. So each individual step is called an elementary step. So in this example, you have two elementary steps, step 1 and step 2. Here's your overall reaction that comes from these two steps. If you add these up and cancel stuff that are on the same on both sides, just like we did in Hess's law, you should come out with that as your overall reaction. So if I get rid of this because it's the same on both sides, and I add up everything else, that's exactly what I have up at the top, because I got rid of the stuff that was the same on either side of the arrow, and now I have my overall reaction. Okay. Molecularity is the number of the reactants that are involved in each elementary step. In our example, step 1 is bimolecular because I have two reactants. Things are mostly either unimolecular or bimolecular. You every once in a while get something that's termolecular, but it's not that common. Usually each individual step just has two things that are coming together, or maybe one thing that's falling apart. So step 2 here is also bimolecular. If you are asked for the molecularity, you just have to look at each step and tell me if there's one or two things that are reacting together. So they're both bimolecular here. An intermediate is something that you form in one step, so it's a product, and then it's used in another one, so then it becomes a reactant. I don't know if this is a great analogy, but I always kind of use a cake. initially you have to make the batter for a cake. So you put everything into a bowl and you mix it up, right? So that's step one. And your product from that step is your batter, all mixed together nice and smooth. Then you put that product into the oven and then it has to cook. And so now when you get that out, it's a different product, right? So your batter you made in the first one and then you used in the second step to form your final product, which is your cake. It's not perfect, but that's what I'm talking about. So something that you form in one step and then you use it in another step. So if we look up step 1 and step 2, something that I form in one step and then I get rid of is my HI. It's a product, and here it is again as a reactant. So I formed hydroiodic acid, and then I used it in step 2 to form my actual products. So I won't see it in my overall reaction, but it forms and it's there and then it's used. That's an intermediate. So HI is my intermediate. A catalyst is something that you add, so it's a reactant, and then at the end of your reaction, it's in the products, unchanged. So it cancels out, but it's something that you would add and then comes out at the end. This particular example doesn't have a catalyst, but we will do some that do so you can see the difference. All right, so let's look at this guy. Is this the one we just did? Oh, it is. Okay, well, I pretty much told you all the answers already, but we'll just do it again. All right, so HI we know cancels. Add these two up. There's my overall reaction. Determine the intermediates and or the catalysts. Well, because anything that you cancel out, it's either an intermediate or a catalyst. You just got to figure out which one. In this case, because we formed HI and then we used it, we know that HI is an intermediate. You will have some problems where you will see that these are labeled as one slow and one fast, or maybe two fast and one slow. And these are your elementary steps of an overall reaction. The slow step is what we call the rate determining step. This is the step that takes the most time. So that's going to determine how fast or slow your reaction goes. So let's think about you like driving to Massasoit, and we'll think about it in 3 steps. So one is you walking from your house to your car. Okay, so there's step 1. Step 2 is your car ride. And step 3 is getting out of your car and walking into apparently jail, Massasoit. If you were gonna, tell someone how long it takes you to get here, you're not gonna be like, well, it takes me 30 seconds to walk from my door to my car, and then it takes me 26 minutes to drive there, and then it takes me 45 seconds to walk in. No, you're gonna be like, it takes me like 20, well, I would probably say 20, 25, because I tend to underestimate how long things were gonna take me, but whatever. You'd say, yeah, it takes 26 minutes to get door to door. You're not gonna consider you walking to the drive, to your driveway and walking into school. It just doesn't make sense because those are insignificant compared to how long it's gonna take you to drive. That's what this is doing. You have one slow step. The other ones don't matter. They're fast, they're not gonna affect how fast your overall reaction is gonna go. And so any slow step is called your RDS, or your rate determining step. And that step is going to determine the rate law. So you're gonna get your rate law information, rate raw. Okay, law info from your rate determining step. Okay. So here's just an energy diagram for something that's a two-step mechanism. So here are your reactants. They have to go up one activation energy barrier. They form this transition state. That transition state is going to fall into an intermediate, okay, which happens here. Then those intermediates are going to react again into a second transition state, and then they fall into products. Because this one has the higher activation energy barrier, this one is your rate determining step. This one's much lower, and so it's not going to take as much time. That's where the holdup is. It's not the second one. And so when we talk about the rate determining step, it's going to be step 1. So step 1 determines the overall rate. Okay. The rate law is dependent only on the slow step or the rate determining step. So I'm going to let you guys do this one. Pause. I think you can do it, and come back. Let me know. Okay, the only one, oh, there's 2 C's. Just kidding. The only one that I think that you wouldn't know how to do is D. The rest of that I think you could do. So the overall reaction I have written is NO2 plus CO goes to NO plus CO2. I got rid of NO2 with another NO2. There's one still there. And so sometimes this would be written like 2NO2 here. And that would be okay, but they wrote it like this because we are trying to flesh everything out. And so you do that by just showing everything out. So you'd still cancel one NO2 with the other one, and then you're gonna leave one because he doesn't have anyone else to cancel with. NO3 cancels with NO3, and then you leave everybody else. The molecularity of each step, they're both bimolecular. First one, NO2 is reacting with NO2, and then the second one, NO3 is reacting with carbon monoxide, and so they're both bimolecular. What are the intermediates and catalysts? So we had to look at everybody that we crossed out and see what's what. So NO3 we made, and then we got rid of, and then we used it. That's the definition of an intermediate. It's our cake batter. We made it, we used it. NO2 is a catalyst because we put it in, but then it just came out the same as it went in. So it started out as a reactant that I put in, and it comes out without changing its form, which is the definition of a catalyst. So NO2 is your catalyst. So NO3, you see it here, then it's used here. NO2, you put it in here, and it comes out at the end. Okay, so rate law. How do we do this one? Okay, so I find my slow step. I'm going to write this over because I wrote all over it. So I started it, and then I realized that we didn't really talk about it, so I'm going to go over it with you. So what you do for this is you literally just take the reactants and you bring them down into your rate equation. So you get rate equals K, which you always have, and then concentration of NO2. Since there are 2 of them, and sometimes you would write it just like 2NO2, now you can use the stoichiometry as your order. Okay? And so the order of this is 2 because there are 2 NO2 molecules, and you can use it as your order. Let's say, for argument's sake, the other step was the slow step, right? So let's say that NO3 plus CO, let's say that was the slow step. It is not, but let's say it was. Your rate law would then be rate equals K NO3 to the first power because there's only one of them, and CO to the first power because there's only one of them. Let's say this was your equation. That goes there. Okay? So your stoichiometry can be your order of just the slow step to determine your rate law. This one, just be careful. There's a lot of HOBRs and HOOBRs. And so, yeah, just be careful doing this one. Pause, come back. Okay, here it is. Check your answers. Make sure it makes sense. All right, the last thing we're going to talk about is the Arrhenius equation. So the Arrhenius equation basically will relate rate constant to activation energy barrier at a given temperature. Rate constant is temperature dependent. So if you are running a temperature dependent study where I'm going to measure the rate at 0 degrees, at 20 degrees, and at 40 degrees, say, your rate constant will change at each different temperature. If at 0 degrees you run a series of experiments where you change concentration, your rate constant will be constant because you're doing it at 0 degrees across the board. So as you increase your temperature, your rate is going to change. Usually it will increase. And so the Arrhenius equation just kind of relates all of these different parameters to your rate constant. So here's your, we're not going to really have to use this, but this is the relationship. A is what we call a frequency factor, which is essentially the number of times the reactants approach the energy barrier per unit time. So it's saying like this is how many times that these things bump into each other. Here's how quick they can get to one another in whatever solvent you're in. And so as they, quote, approach the activation energy barrier, that's just saying they bump into each other with an appropriate amount of energy and they could potentially make products. Do they do that 100% of the time? No, but here's just the number of times that happens. And then this second part of it where you have the exponential factor to the negative EA. Remember, that's your activation energy. That's your gas constant. Here's temperature in Kelvin. And that's the fraction of times that are actually forming products. So you have the number of times that things could happen, and then you have the number of times that they actually happen. So that's sort of what this relationship is, and then it all ends up with your rate constant. It's essentially just breaking down your rate constant. How many times can things get to each other and smack into each other? And then how many times does this actually form products? So here's the equation that we need. This looks a lot like the Clausius-Clapeyron 2-point equation. It's based on a graph. Here's the relationship if you were going to graph it. So the idea is that if we plot ln of k on our y-axis and 1 over t on our x-axis, that our slope is going to be equal to negative EA over R, where R is your gas constant. The idea is that if you're given a slope to a linear, like a slope of your linear regression, you should be able to solve for your activation energy barrier. One of our problems coming up, we're going to be given a slope and we just have to essentially multiply by negative R. And that will get us our activation energy barrier in joules. What we are more interested in is this guy down here. And we're going to have 2 rates, 2 temperatures, an activation energy, and our constant R we always have. Usually we're just finding our rate constant at the second temperature. So we'd be looking for K2. You could also be given the rate constant at both temperatures and be solving for our activation energy barrier. All right, let's do 16 and 17. We have y equals mx plus p. So here is our linear regression. Determine EA. So all I have to do here is say that 1.12 times 10 to the 4th is equal to negative EA over R. So I multiply both sides by R. To find my activation energy. So I'm going to finish this one up here. So I take 1.12 times 10 to the 4th times 8.314 and I get 93117, and that's in joules. It didn't ask me for kilojoules, but if it did, I just say it's about 93.1. And that's my EA. Simple. Just take the slope out. Oh, I have to multiply by negative R because that's negative. And then it will all cancel out. So that negative will cancel out because of this negative in the equation. Okay. Now we have a 2-point problem. We have 2 temperatures, 2 Ks. We have to find EA. I'm just going to let you guys do this. I feel like you can do it. Pause, try 17, and I'll have the answer for you. All right, so I plug my numbers in, and then that's what I get for my answer here. And I have it in joules and kilojoules. Okay, just make sure that you are taking this step by step. You want to do the division and then take the ln of your 567 divided by 2.57. Divide that out, then take ln. That's kinetics, guys. So good luck.